a little bit late, but I'm sure Patricia and I will be able to improvise previous show for you as a beginning. So, to start with, I want to thank you all for being here, and very many thanks to Dr. Diego Solis, who is, as you know, the director of this institute. Without his support, we wouldn't be able to be actually right here. We got on the screen for the World Cup, but we got it just before this event, quite literally 2 days ago, if I'm correct. So, the way that we would like to start is with a very interesting story of how everything started, how this idea came, and for that, I need not be the presentation, but
Thank you very much. Thank you, Luis. Let me introduce a little bit the context before. So, yeah, this is, can you check? Yes. I wish. Anyway, how can I start? Because, well, this is important, and now it's important, today it's important, because currently, well, we have some numbers that these statistics scare us. Well, if we can see here, depending on the stage, women presence in all the field research, starting from undergraduate, bachelor, master, okay, even PhD, we have almost 50% presence in all the fields, even for example, here. But when we take a look to the STEM, so science, we can see the difference. So even in this case, maybe, okay, women are not liking science, maybe, I don't know. Well, this is changing, but even is more scared when we check here, researcher, lecturer, and full professor and senior, this is the glass saying that make really the woman afraid. Why is happening this? Well, I don't know exactly, because for me, in some cases, I'm used as a kind of a luminary or representative woman that, well, reach this or overpass this stained glass. But many other people is not really reaching that. What is happening, no? Even I can show you here, well, we're improving, it's not that bad, positive. Well, this is the fourth, in the first one, in the survey conference in 1924, there was only one woman, Marie Curie. Okay. It was easy to be there. Whatever. I mean, but look at this year. Well, I take a look to the conference. Nobel Peace Symposium in 2023 in Karlskoga in Sweden. So here you can see the picture, really nice. 11 women over 29 speakers. If we consider also the chair, this is the most, 14 over 38. This is in 2023. This was the history of the Nobel Prize. So in this case, it was like discussion about who can be the Nobel Prize in the next year. And well, apart of this, well, we were deciding there, but we have a lot of fun there. But of course, we have even more things. This was the history of course, the Nobel Prizes this year. Susumu Kitagawa, Richard Robson, Omar Yadi for the development of metal organic framework. But this was also the day here in this conference, where we really start this conference. We were discussing in the gala dinner, Illich and me, please
Yeah,
help me to remember this.
yes, I do, I do. After a few sodas, we were discussing about how great would it be to have an event where the spotlight would be for you women, and particularly in Mexico, because we believe that if more of our female students have this representation, would be very inspiring, coming from all over the world and from different parts, of course, of Mexico. I'm very happy to have, for example, people from Monterrey. Thank you very much for coming, and other places. And I think it's not just for women, as we describe it in the motto of the conference. I'm so happy to see some of my male students, all the male students that I don't know. And I think this is a celebration. This is something that we should be very happy and proud of it. And with that, are we ready? Okay, it's time for Susumu. Thank you, Patty.
Thank you.
Thank you, guys. Thank you.
Only one important thing. Here, this is the visibility for women, but we want to have an informal meeting where the students, with all the people is participating, that this is really a networking, interactive conference, okay? So please, be active.
Okay, Susumu, can you hear us?
Yes,
First of all, congratulations and thank you so much for being here. This is not recorded, just for the record, this is live. If I'm not wrong, it's 8 o'clock in Japan. So thank you so much. Susumu, the floor is yours. Thank you so much.
thank you very much. Uh, Good morning, everybody. First of all, thank you very much for kind introduction and also the inviting me to this wonderful uh, this conference. So today my title is Dynamic Framework, Chemistry of Transformation and Empowerment. This is my journey with a mind prepared of assembly, space, and mobility. Oops. What? Just one. Okay. So my talk contains three parts. The first one part, just look at the current world. So this is geological timeline of our Earth. So we are now standing at the late Holocene. So this late Holocene started at 4,250 years ago. So now we are standing here. But the last year, I read very interesting papers published in PNAS, and the Professor Kuae and Doi and the other collaborators. So this paper said the number of anthropogenic fingerprints began to increase abruptly from 1952, around 1952. So rapid increase in the traces, Eurification, chemical pollution, the shift to synthetic fibers production, and nuclear testing in all regions of the world almost simultaneously. So they conducted cluster surveys dating back 7,700 years at 137 points worldwide. Here, North America, Europe, Arctic, East Asia, Oceania, and so on and so forth. So this plot shows the vertical axis is the cumulative amount of all the anthropogenic materials. So, and this show the correspond to this area. So this line increases. All line increases. We look at the just a differential curve here, red one. You see clearly show that all this value abruptly increase around 90, 50, around this. So that means we are now facing a new geographic age. So the human created the new technologies, but simultaneously increases a lot of pollutants and the bad materials. So another things, as you know, in 19th century, the people created new technologies that consumes a lot of energies. So people use solid coal this time, and then the 20th century, liquid petroleum, as you know. What about the 21st century? We think gas materials are widely used, and for instance, in natural gas, in biomass, and also the air and something like that. So we think we are standing at the gas age. However, humankind is still not in control of gases. So these are small molecules showing the gas state at ambient conditions besides water, but water still the form of the vapor in our atmosphere. So these gas substances are strongly correlated to environment, natural resources, energy, even in the case of life. However, we just look at the underground resources. So we use the underground resources to produce a lot of the materials and fuels and so on and so forth. We are facing the lack of resources and also global warming. So what we should do for the future? So we have to think about the ubiquitous resources for all materials. That is the future of our world. So this is a beautiful scenario, but we cannot still realize. So the air contains a lot of the useful elements: carbon, oxygen, nitrogen, hydrogen. So if we could capture these materials and separate into useful our target gas substances and the concentrated and stored, then we convert these gas substances to the useful materials. For instance, in the case of fuels, once fuels combusted into the air, but we can recycle again. So this is very beautiful scenario, but we cannot realize right now. So we have to think about the near future, about this kind of the science and material and the technologies. So just I said, we are now standing at the gas age. However, gas substances, and we are very difficult to handle gas substances. They easily diffuse and they are invisible and they are short life in certain case and toxic. So to handle these gas substances, we have to create new porous materials. By using porous materials, the separation, storage, conversions, these fundamental processes are very important under mild conditions. And that's the point. So we are moving to the part two, the chemistry of creating nanospaces. So this year we announced in this case for the development of metal organic frameworks. So needless to say, these materials are called metal organic framework, MOFs, or porous coordination polymer, PCBs. So very from the component we can construct the various kinds of the framework. So today this symposium is very important for the empowering the female scientists. So for that purposes, just I want to mention about my history, how I began the chemistry of metal and frameworks and arrived at the creation of special material chemistry. 2 points are important, three foundational concepts I had, and also the research institutions and the environment. So let's start this one. I learned the science in the Kyoto University. This is located in Kyoto, and I spent undergraduate graduate course. I learned the quantum chemistry and the spin dynamics. So that is the physical chemistry. I learned physical chemistry. Sorry, this is Chinese character, but you can understand. This is the academic tree of the Department of Chemistry, Graduate School of Engineering. So this is engineering. So the founder is Professor Kita. This is first generation. The second generation here, he is Fukui, Professor Fukui. He was awarded Nobel Prize in the quantum chemistry. And this is the second generation. The third generation here, and the Professor Yonezawa found the laboratory. I belong to this laboratory. And the 3 years senior, Professor Yoshino, he was awarded Nobel Prize in 2019 for the lithium batteries. And I belong to this group. And that time, it is a part of an engineering faculty, engineering. But its academic culture is like this, intellectual freedom, very free about the thinking of the chemistry, and a strong emphasis on fundamental research. So usually the engineering is just application, but this department and the faculty, we focusing in the just fundamental research. This was very, very nice for my career. So let me introduce the three important keywords. But for introducing this, before introducing this, I want to say the chance favors the prepared mind, following the Professor Louis Pasteur. So this is very important, not by chance, but how a questioning mind opens the door to science. That is very important. The assembly, my case in assembly space dynamicity. So once again, the three keywords. In the case of assembly, this concept is very important when I was undergraduate students, because just I learned the proteins. The human body contains more than 100,000 types of proteins, but all proteins constructed from only 20 types of amino acid molecules. So assembly is very important for the function and the use and the structure. The other things I learned statistical physics, and this shows most of the audience knows the thermodynamics. This is the macro scale, very beautiful theory, but by using this Boltzmann equation, we can link this is the macro scale to the nanoscale. So the assembly is a very important concept for me. So next space, later on, I will show you. And dynamicity is also very important. So when I was a high school student, I learned the Greek philosophy. In particular, I quite impressed in the Heraclitus, the notion. No one ever steps in the same river twice, or everything flows and changes, Pantalei. So everything changed. This is very important. Also, I was born and grew up in the Kyoto, so it's a very historical city, and there is the very famous essay written by Kamono Chomei, and he said also the same things. Everything flows. And the other things is this is also the Heike Monogatari tales of Heike family. And so this also shows that. Also, we are Japanese, were influenced by the Buddhism. So this is reincarnation. So when I was the graduate student, I learned about the spin dynamics using the nuclear magnetic resonance. So all knows about the magnetic resonance gives information about chemical shift and the reaction time. So I was very interested in the relaxation time because this is the non-equilibrium processes. So we studied this kinds of this histidine cobalt complex. So in the solid state, we had a very beautiful static this kind of structure, but in solution, in particular in the aqueous solution, depending on the pH, these functional groups exchange with the water or the hydroxide or something like that. So very dynamic. So this is a kind of root of the function of proteins. So I studied this dynamic, the aspect using and the NMR relaxation times, and I observed this time scale. And this is just my first paper. So the concept of motion lingers in my mind like a faint flavor, still faint flavor. So Kyoto University and also we had a Nobel laureate, and this is Hideki Yukawa, physicist. So he loved to read Chuang-Tzu. Later I'll show you. And also this is the philosopher. He created new philosophy, Eastern philosophy. That is, he studied nothingness. And then when I was undergraduate student I look around the bookstore, I found this very interesting book, World of Genius, written by Hideki Yukawa, already I introduced. And the number three, volume three, he wrote the Chuang-Tzu. Chuang-Tzu said, the usefulness of the useless. Everyone knows the usefulness of the useful, but no one knows the usefulness of the useless. So for instance, a kind of space, nothing here, looks like a useless. But if we think this is a space for ions, molecules, and so on and so forth, so that means in a space, we divide this space into the small one, and this is also the space. And when we accumulate this kind of space, this is just exactly the porous materials. So most of the people focusing on the framework, but the space is also important. So the creation of space where molecules and ions can be freely manipulated. This is the usefulness of the useless. So how we can make this kind of framework? That is a big issue. And in the case of large scale, and you see, this is the very famous temple in Kyoto. this temple has a big balcony. So from the balcony, you can see the Kyoto city. So this is constructed from the 139 pillars of Zelkova, and no pegs were used in this construction. So that means in the macro scale, it's easy to construct like this. But in the case of nanoscale, how we can make it? For instance, this is still macro scale, but we can imagine how we construct this kind of framework. So in this case, we use the magnet. But what about the magnet in the nanoscale? So we are very lucky. We have the coordination bond as a magnet. So we constructed using this magnet like this. So we can expand the structure three-dimensionally. So we select the organic molecules and metal ions, so they construct just mix two solutions. In the mix, in the seconds, we can get like this. So the various type of framework, all the people are very familiar with this kind of framework. And from the jungle gym type structure, this is conglomerates. So, and this is 1 micron crystal. It's very difficult to see, but we can determine the crystal structure, of course, by using X-ray crystallography. So you see the 1 unit around 1 nanometer. That means in this side there are 1,000 cavities, and this side 1,000, totally 1 million channels per 1 micron crystal. So that's enough. So using this kind of the porous structure, the gas molecule accommodated in this fashion. So that this CO2 molecule, for instance, is accommodated in a very small channel. So in the case of zeolite, the inner surface area around 500 square meter. But in the case of the activated carbons, the half of the football field in the MOF materials, almost the football field or more. So that means very light materials. So what about the name or terminology of this type of materials? The coordination polymer has been used for over 100 years because the Professor Shibata, they wrote a paper using the coordination polymer, in this case French, but the already used. But these materials, a long time ago, people are interested in this. So we moved to the Kindai University. This is a private university, and we studied Kappa 1 chemistry. So this is big change because my background is physical chemistry, in particular in the quantum chemistry, but in Kindai University, we focusing on the Kappa 1. Kappa 1, the ion has a D10 configuration, no DD transition. That means the colorless mostly, the no spin. So looks like a very boring ion. So useless like that. But MOF PCP began with Kappa 1 chemistry because in the 1959, the Saito synthesized these kinds of the network structure, determined the crystal structure. And also the Richard Robson and synthesizing the diamond-like structure using Kappa 1. So Kappa 1 is a very important ion to get the beautiful single crystal. So I also studied this kind materials, and one day we found the porous structure. This is the honeycomb structure. What is interesting is the anion in the cavities, anion incorporated, but simultaneously the organic molecule also incorporated. that is a very, very big the impression that time. So my chemistry, before that, my chemistry studied the dense structure because this kind of network structure looks like a molecular wire or a molecular magnet. So the dense structure is very important in these properties. But if we look at the porous structure, that's completely different. So we studied also studied the porous materials from that time. So once again, this is the copper one materials, and mostly this is the neutral ligand. So totally the cationic framework is obtained. So to neutralize the charge, the anions are incorporated in the cavities. So the only my case in organic molecule also incorporated in that case. So that is the big issue. And the other things in the kappa 1 organic ligand, neutral ligand binding is weak. The energetics is around the 100 kJ per mole. So because of these properties, the framework is not so strong without gas molecules. So the target is the organic based crystal possess stable nanopores. So we move on to the Tokyo Metropolitan University, that is municipal university. So here we studied this type of materials, and that is the cobalt 2 plus and bipyridine and nitrate. In this unit, nitrate directly coordinate to cobalt. That means we can get the neutral framework. And also the Mayagi and the carboxylate used and obtain the neutral network structure. So that means the cavities can be used for the gas molecules. So we carry that gas sorption like that, and also gas sorption like that. So our compounds and the Tanguan group structure and to examine the stability, the Matt Rosinski and Cameron Kepler to study this thermal stability, and here and the crystal lattice parameters are very constant up to the 360 Kelvin something. So that materials is stable for the gas sorption. So we are now standing at the second generation compound. This material showed just like zeolite. So we obtained this kind of second generation compound, but the porous material community, the people said, why we have to use this kind of the expensive and complicated porous compound using organic molecules. So we need to seek the very special, unique properties in the case of MOF. So that is third generation compounds. So move on to the Kyoto University again. So I was so lucky because the Kyoto University is close to the spring weight, the facility, just synchrotron radiation facilities. And also we get the instruments for studying the porous materials. So in the announcement and the Nobel Prize in Chemistry 2025, my achievement in the first one is just to create the robust MOF materials using gas sorption. The second is the flexible framework. So I was so pleased to hear that because I was most interested in these properties. So once again, the Heraclitus said, no one ever steps in the same river twice. Everything flows. So that is a change. So from static to dynamic. Oh, this is the toy, you see, and the component does not change, only angle change. So this is a good hint to create the porous materials with flexibility. So this is my focus in after that. And in the 98, I predicted the presence of this type of flexible framework. And just after 2000, this type of the flexible framework have been found. The first one is the layer type system, and this is hinge type. This is interpenetrated case, and this is expandable case both. So the quite the impressive the year. So let me introduce the one example from my compounds, the copper 2 plus and the dihydroxybenzoic acid. By building, we can get this kind of the interdigited system. So the layer distance can be changeable, and depending on the gas molecules. So thanks to these properties, even at the room temperature, we can distinguish the supercritical gas substances. So what is interesting, they showed a sort of the sigmoidal curve. This is completely different from the conventional porous materials. So the FX Kudat, calculated the energy thermodynamic energy, the open form and the closed form. So what is interesting in the difference in this free energy is around 4 to 5 kilojoule per mole, very small. That means this is a sort of the cooperative effect phenomena. But anyway, since then, the people said the porous material should be static, rigid. But this is a big paradigm shift from the static to the flexible system. So thanks to properties, we obtain this type of sigmoidal curve. So we have a 3G type system. So we call this is soft porous crystals. Because this kind of properties occur in the case of organic aggregates and also the so-called covalent organic framework and so on and so forth. However, we are very much interested in the initial compound that is 1997. Already I showed you Tangen group structure here. So in the case of the activated form, the pore size, the cross section is like that. So this is actually this is the smaller than the methane or nitrogen. So still we had a question, can it absorb gases even though the pore size is smaller than the gas molecules? So we revisited these materials because right now we have the fantastic facilities and the instruments to characterize the structures and the functions. So this is the activated form, and you see the channel is like that. So the big pore and big pore, they are connected to the small pore. This aperture is smaller than the gas molecules. This is the structure, but we carried out gas option. This is the CO2. Even at room low pressure region, the smoothly absorbs the CO2 like this. This is the first step, and the abruptly change in the second step. So each state we determine the crystal structure. This is the empty form, and this is the partially adsorbed form, and the final stage is like that. So all shows the gas smoothly adsorbed in this way. So what happening in that case? Maybe local flexibility and global phase transition happens, and in this case. So this is once again side view of the channel structure. This is constructed by pyridine and nitrate like that. So this is the cross-section part, the bipyridine, and nitrate like that. So bipyridine can move like this, rotate, like just like this kind of door, and accommodate gas molecules. We call this is the porous squeezing diffusion mechanism. So this mechanism happens in this case. Oh, sorry. So we can say we have already found the soft porous crystal and flexible porous materials in 1997. That is very impressive for me. So the second generation and third generation compounds show the various type of the functions. It's quite the fantastic the future uh, feature of our compound. So nowadays, as you know, we have the more than this 122,000 and also the 130,000 more materials. Oh, sorry. Then I would say the at the beginning, I showed you the conceptual keywords. When I was a undergraduate student, the assembly, space, dynamicity, all keywords are realized in the 3G system. So th- that is my an interesting story. And so but we have to keep going. So we have to see this framework. So one thing I want to emphasize on these properties, because this material is constructed from organic molecules and metal ions. So in addition to global dynamics, the local dynamics exist. So the how local dynamics contribute to these properties and the global and local dynamics contribute to these properties. So acetylene sorption, as you know, we studied this acetylene sorption, but acetylene is very dangerous at the 2 bar room temperature, abruptly explode. So to store pure acetylene is a big challenge. And after our work, the many people studied the acetylene sorption. This is the highest capacity, but this is saturated amount. So when we look at the desorption, the recovery process, so as far as type 1 uh, form, we cannot get a lot of the recovered the acetylene. So we need to have this kind of sigmoidal curve. But in the case of acetylene, it's quite the severe condition because the pressure region should be from 1 bar to the 2 bar. So it's possible to get this kind of things? Yes. This answer is yes. So we already get this kind of the sorption profile like this. The 1 bar and 1.5 bar, we obtain this kind of sorption profile because of the flexibility. So the second one is the local dynamics. How local dynamics contribute to the gas sorption. So this is a big challenge, but we look at this is we constructed the framework using this type of the separation, that is H2O and D2O, the water isotopologues. The properties are very close to each other. So that means this is 100-year the puzzle, how we can separate efficiently these two materials. So after the discovery of these wall and this distillation and the electrolysis and the sophisticated method recently, but still separation factor is 1.05, 1.02, even recently in this case is 1.2. So still we need to have the mechanism, new type of the theory. So we studied this kind of the big pore, small pore, big pore, small pore channel system. And in a small pore, we put this kind of the local motion. In this case, we call this is the dragonfly type motion here. So we studied obtain this kind of pore structure like that, and big pore and small pore. So, and the H2O and D2O diffuse in the pore. This is the adsorption kinetics. So please look at this very clearly. The differentiated. You see the H2O smoothly diffuse in comparison with the D2O. But in the case of zeolite, activated carbon, ZIF7, FMO, and this is the other MOF materials, HKUSD1, all materials showed exactly the same, the diffusion, but our case is different. So we succeeded in getting this type of separation, and our case is the separation factor is 4 to 200 at room temperature. But in the factory, the current factory system is just 1.2 to 2 and more than 200 degree Celsius. So by using the local dynamics, we can see very fantastic the regulation. So and the part 3 is the time is almost up. So I want to introduce in the world there are startups, more than 51 startups, to producing the MOF materials in the low cost and the scale up. And so this is a good news for the just the commercialization of our materials. And so the R&D stage to the pilot, the demonstration test to the commercialization in the startups showing very fantastic the future. So finally, in a few slides, this is a message to the young scientists and also female scientists. So we think the 3 keys to success we have. So this is challenge character, but look at this one: luck, stubbornness, perseverance. So luck. So at the beginning, I introduced the Louis Pasteur. He said, in the field of observation, chance favors prepared mind. That's very important. So it's not lucky to think that God is the only one who knows what is going on, and therefore we should rely on Him. Still, by obtaining information, learning, and working diligently on our own, we will naturally approach good things. So my case is the 3 keywords. I learned the 3 keywords, and I follow 3 keywords. I carried out my chemistry. So please believe yourself, and luck is just a prepared mind. And the second, stubbornness. So it is not the ability to understand and accept immediately. So smart person immediately understand, but this is the way of the follower. So the pioneer create new things, but the ability to question and take time to digest without receiving immediately, that attitude is also very important. Con means just never give up. So patience and never give up is very important. So that's my message, Undon Kon in Japanese. But anyway, my dream and people's dreams, life by use of mist. Mist contains the air and the water. So the age of air gold, now we are age of air gold. So please create new materials for the future. So that's my talk. Thank you very much. for your kind attention.
We really want to thank you, Susumu, and congratulations again. It's been absolutely an amazing talk, and we are very lucky and fortunate to have you. Thank you.
Thank you very much.
Thank you again. Okay. Now, we have a special presentation by Professor Catherine Merica. Thank you very much.
Good evening. It is an honor to be here in Mexico among colleagues who are committed to building our future together. I'm grateful to the organizing team, women and men working together to spotlight the contributions of women in MOFs and beyond. Our collective message from the organizing team is simple and powerful. Science is a team sport, and the best teams are diverse, inclusive, and accountable. The architecture of metal organic frameworks is an excellent metaphor for universal empowerment. We design structures to welcome guests, select strategically, and respond reliably. Our community aspires to be the same, open, selective for excellence, and responsive to evidence on diversity and inclusion. The problems that MOFs target, clean air, pure water, efficient energy, and human health, are global challenges that are complex and require the full participation of global talent to address. Working together across national borders, as well as interfaces of academia, industry, and government, is an important effort to accelerate both discovery and equity. When we widen who builds, we widen what is possible. This conference aims to spotlight the contributions of women in science to counteract historic barriers to access, credit, and visibility. Through panels on mentorship, work-life balance, and career options, our goal is to move beyond aspiration and to build a living ecosystem where empowerment is practiced and not merely proclaimed. I want to contrast this vision with a stark warning by the Mexican muralist Jose Clemente Orozco depicted in his mural, The Epic of American Civilizations, which is housed at my home institution, Dartmouth College. This panel, entitled Gods of the Modern World, shows us academics and figures of power who have turned their backs to the world as it burns in the background, while they stand passively to observe the birth of dead knowledge. This is not our vision. We seek a living ecosystem, vital, inclusive, and responsive to the needs of the world. While the spotlight of this conference shines on the contributions of female researchers, our male colleagues are present here as allies and visible co-architects, initiating ideas, framing concepts, holding space, opening doors, securing sponsorship, and taking care of logistical organization. Even the word empower contains the word we, symbolizing our collective intent of men and women working together to design fair systems, share information transparently, and engage in open conversation. Empowerment means shared power put to work, structures that distribute power, and skills that make it effective. It is not a favor, a feeling, or a power pose. It is a leadership strategy for tackling global challenges that are greater than any single lab, university, or country. Just as in science, though, good intentions are not enough. We need evidence to guide and structure this process. And as MOF scientists, we love evidence. We characterize with rigor, we validate with controls, and we optimize the structural integrity of our materials through extensive iteration. Empowerment deserves the same rigor. Programs that are grounded in data, iterative design, and accountability have the potential to compound over time. The organization of this conference models structural accountability, clarifying roles so that the responsibility is visible and tied to power. This design mirrors the evolution of our own field. Reticular chemistry in the 1990s transformed modular synthesis into an architecture for function, just as universities began confronting inequities in science around the same time through structural accountability. I would like to highlight two notable examples that have shaped that era and also influenced my own career trajectory. At MIT, the 1999 report on the status of women faculty in science, led by Nancy Hopkins, a biology professor, exposed systemic inequities in space, pay, and resources. What made this report transformative, though, was not just the evidence, but the institutional response. Based on the efforts of women and men who worked together to put together this important report, MIT created formal mechanisms to monitor, prevent, and correct such disparities. Within a decade, women faculty in science and engineering nearly doubled, with measurable improvement in climate and leadership representation. Transparent data policy change here yielded durable progress. Actually, as I was preparing this talk, I reached out to Nancy Hopkins. I wrote her an email as I deeply admire her for putting her own career on hold to advocate for the equity of women in science. I thanked her for making the invisible visible and for showing how evidence can move institutions. She wrote back the same day, reminding me that change happens when people work together and when leaders are brave enough to listen. She called it a bit of a miracle in how the whole thing worked out. And her words reminded me that this work must continue, both for the sake of our science and the structures that sustain it. At Harvard in 2005, the case of President Larry Summers, who suggested that women's underrepresentation in science was due to innate differences, triggered a historic vote of no confidence by the faculty. This was an act of governance, making and holding power accountable to values of equity and respect. In response, Harvard created university-wide task forces on women in science and committed resources, actual money, to hiring, dual career support, childcare, and mentoring. Here, structural reforms turned conflict into constructive redesign. These are not just symbolic moments. These cases represent evidence that when we name and formalize structures, things actually change. Those reforms reshaped the academic spaces that allowed many of us, myself included, to move from surviving to thriving in a leaky pipeline. These ideas about structure and power are not theoretical to me. They touch on very personal experiences of navigating the growth of my career with the growth of my family in parallel. When I was a graduate student at Harvard from 2004 to 2011, there was no formal maternity leave or parental leave policy whatsoever. Forget paid, just no policy whatsoever. Navigating that ambiguity while having my first child during my PhD training required immense personal negotiation within an undefined system. A reminder that when structures are missing, power imbalances can amplify. Although it worked out in the end, we're all good, it was my first clear experience of inequities in science that women can face when fundamental supports and policies that are obvious in retrospect are completely missing from the institutional framework. Only a few years later, as a postdoctoral fellow at MIT, the landscape was very different. Supported by a fellowship from the National Institutes of Health, I had access to clear, paid parental leave policy. That structure transformed that experience from one of uncertainty to one of dignity and clarity. Those experiences showed me, in the most personal way, that empowerment is not abstract, and it begins with structures that honor human lives. In parallel with these cultural shifts, framework materials took off with significant milestones that we got to hear already today from Susumu's talk, as well as some that I'd like to highlight of MOF5 in 1999 and COF5 in 2005, because they parallel some of the examples that I just presented of structural accountability. Women were there as co-architects from the start. Note Hailan Lee as first author on the 1999 MOF5 paper in Nature, and Annabelle Benin as second author on the COF5 paper in Science, all under the guidance of Omar Yagi in this case. This parallel structure is more than timing. MOFs showed that deliberate architecture yields predictable properties, and structural accountability showed that deliberate policy can yield fair outcomes. In both cases, when we design the framework, pores and linkers in one, policies and metrics in the other, we can convert potential into performance and broaden who gets to participate. A generation later, the field has flourished and diversified. 2 generations ago, co-education at elite universities was still new. Dartmouth admitted women for the first time in 1972. This is not that long ago. And other elite universities making similar changes around that time. Today's shared classrooms and laboratories embody how structural change can alter and expand who builds our scientific future. We have come a long way, and many barriers have fallen, but others persist in quieter forms. To move through them, we need not only opportunity, but courage and understanding of how power works to navigate complexity with clarity. Unlike crystalline materials, power has a somewhat hidden architecture. At its core, power is based on agreements that are forged through conversations inside relationships. Every solid institution, marriage, law, universities, is a crystallization of such agreements in writing. For generations, these conversations took place and agreements were made without any women in the room. Having a seat at the table now, though, presents us with both an opportunity and obligation to re engineer those structures. That means showing up as skilled conversational architects, framing issues, stating needs, negotiating trade offs, writing down decisions, and assigning task owners and dates. When we contribute in this way, skillfully, consistently, and confidently, we convert presence into influence and renovate the system to serve us all. In theory, power is the reliable capacity to shape outcomes through influence. In practice, it is the ability to lead the direction of conversation, to achieve consent and consensus on specific outcomes, and to advance progress through collaboration. It is not Machiavellian conquest or authoritarian dictatorship. The misuse of power, coercion, manipulation, covert control, gaslighting, stonewalling creates fractures that ultimately lead to collapse. These kinds of tactics bend reality, undermine integrity, and lead to brittle architectures that will ultimately crumble under the test of time. As scientists, our first obligation is to what is real, experiments that test claims against the world, anchored in ground truth. Power should be held to the same standard, anchored in values of honesty, transparency, integrity, and accountability. Used in this way, power is creative, not destructive, and it can expand the freedom of thought and action rather than constraining it. And it can foster synergy that can lead to outcomes that were previously unimaginable. Using power in this way, we can build durable architectures that not only stand the test of time, but compound for future generations to build upon. So, how do we translate this conceptual framework into actionable outcomes? Simply put, empowerment is shared power put to work. It involves the combination of structures and skills that let people use it. I'd like to propose an approach to empowerment in the form of an equation that involves multiplication. Empowerment is equal to power shared, structures, multiplied by power exercised, which is skills. This is a multiplication, not an addition. If either term is zero, the product is zero. We need structures and we need people who are trained to use that power well. I suggest 3 evidence-based strategies in how we can train people to improve this process. First is mentored technical training. Technical competence builds confidence. Building skill ladders for core methods in our field, that is glove box work, PXRD, BET, diffuse reflectance infrared spectroscopy, data analysis with clear levels and privileges can formalize mastery. Pairing trainees with mentors who provide feedback on design, data, and writing can ensure calibrated alignment with standards in the field. Documented standard operating procedures, transparent authorship criteria, and written feedback can create visible pathways for growth. In mentored technical training, 360-degree feedback can also transform instruction into collaboration. It can create a dialogue where mentors and trainees can learn from one another, catalyzing a pathway for shared growth and empowerment. When metrics of competence are clear and credit is equitable, young scientists can trust the system and themselves. Second is leadership training. Leadership drives influence, and influence is how power operates. We must teach evidence-based tools for high-stakes conversations, discussing authorship, stewarding instruments, negotiating collaborations, resolving conflict, setting boundaries, reclaiming the floor, and giving feedback. In leadership training and in PhD itself, our goal is to help students to evolve from apprentices to independent leaders. And it is this journey from following to envisioning, from executing to creating that we want to prepare them for. One of the deepest purposes of doctoral training is to nurture the ability of students to think independently and to chart their own course, while learning to share power, collaborating, mentoring, and lifting others along the way. Communication and writing, and through oral presentations, is also an important part of making our research visible. In this case, language itself can be a bridge or a barrier, because oral and written communication shapes how our science is heard and remembered. Access to international conferences and mastery of the English language are not mere privileges. They are instruments of visibility and connection, which are critical for building global alliances and amplifying diverse voices in science. Embedding such training into PhD programs across the globe can turn empowerment from an accidental byproduct into deliberate outcome. Third and final is active allyship. Active allyship and accountability, especially from senior men and women with power, can help junior researchers navigate complex dynamics of power. Allies open doors, create spotlight opportunities, and can also help students find job opportunities. Networking at conferences, such as this one, is an excellent venue for building alliances. Such alliances can help ensure parity in invited talks, promotions of scientific contributions through nominations and awards, and promote equitable distribution of service loads on committees. Along the way, I have been extremely fortunate to meet both men and women who became true allies, people who shared their knowledge, resources, strategies, and encouragement at moments when the path felt uncertain. I'm truly grateful to my mentors who believed in me, especially in moments when I did not believe in myself. Throughout my career, I also met other allies who played pivotal roles in my professional development. Some offered strategic advice that shaped the funding plan for my independent research program. Others quietly opened doors, spotlighted my work, and advocated for me when I could not be in the room. And others simply asked probing questions that elevated my thinking and helped me to level up. The support and encouragement reminded me that empowerment often begins with generosity, and that shared success is the most endurable form of leadership. When allies act, equity can advance much faster than policy alone. When we design for fairness through shared structures and train for competence through shared skills, empowerment stops being an aspiration and becomes a framework that brings more people into discovery and can speed solutions to global challenges. When authority, knowledge, and recognition circulate, we can build durable coalitions that not only stand the test of time, but compound and enable us to solve global challenges associated with decarbonizing energy systems, cleaning water, safeguarding health, strengthening resilient materials ecosystems, and other problems. Progress then becomes much less about who gets the credit and much more about how we solve global challenges and frame our future together.
We are okay with time. Would anybody would like to have a question? All right, so if not,
Thank you, Kat. Wonderful. So very inspiring. One question is also that you mentioned also some institutional support. You have even lived by yourself, no? The difference between the support and absence of support. How about additional, can you maybe propose some additional institutional supports in the universities, for example? Okay. So for really make easier this balance between the personal and professional life?
I think that's a really good question, and it's a really complicated one because we're talking about like disjointed and disconnected support structures across the world. And they're quite different in the US compared to Europe, maybe compared to Mexico. So it really depends what we're talking about. Like in some ways, US is so far behind in the support structures that it offers, and maybe other countries are ahead. And I think it's helpful to look at each other. But certainly, like things related to parental leave is obvious, and parental leave, not just maternity leave for the mother and the father, so that the family can support each other and so that it is equitable. But I think to answer that question, like from my perspective, would have to really look at each specific system. And these systems are relatively complex. And so that's why my emphasis is maybe less on one particular system, but more on the approach, the process we take to deal with those barriers.
But in this case, we can maybe learn from the other countries that maybe have better policies. What do you think, in your opinion, of the countries that could be taken as a to be followed, no? As the yeah,
As like
standard,
a model.
I don't know.
A model. Yeah. I think it a lot of this comes down to personal choice also. Like it is the freedom for example, for a woman to choose how long she wants to stay out after giving birth, or how she may want to balance that process with a partner. I mean, I think some countries that give a year, to take for parental leave, for example, that is a really generous policy. And I think it can be really beneficial for recovery and enjoying like a balanced lifestyle. But then some countries in the US, if you take a year, the feeling is that you get outpaced by competition. And so some women might not want to take that entire time. And they might feel like they're more ready, to enter the workforce after a shorter amount of time, but having good daycare arrangements to take care of the child then becomes more important. So I think it's so nuanced from my perspective. Like I take a very personalized approach that everyone is different and everyone should have the freedom to chart their own course in how the system could work for them. And having options is the best thing from my perspective.
okay. So thank you very much, Professor Marika. Thank you very much. So we have two announcements. The first one, Dr. Professor Solis is going to give us a hello. And then after that, we're going to evacuate the room because there is a fire. No, not really. Because the cultural event is coming, so we need to set up of everything so we can have a little bit of coffee or whatever while everything is being set up, if that's okay with everybody. So with all that said, Diego.
Well, thank you. Thank you, everybody. It's really a pleasure to welcome you all. Bienvenidas, sean todas. It's really an honor to have you here at UNAM. About a year ago, or maybe a bit more than that, Illich presented to me this idea of this conference, and I really thought it was an amazing idea, a very timely idea. And just as the program started to form, And as we started to see the lineup of amazing speakers that all the organizing team put together, it really may make it even better, because what better to combine great science with a great social spirit, and what is science without that social idea, with that really aspiring to improve our society. And just in case the timing wasn't good enough, like what about just having the Nobel Chemistry Prize just being announced about a month ago on MOF chemistry? So it's a really an amazing time. I don't want to say much more. It's hard to follow Catherine's words, but I would just like to really thank the organizing committee. I also have to thank really much all the efforts of the UNAM team. I'd like to thank Julieta, Selig, Alan, Cain, of course, Betty, which has been supporting a lot, and of course, Professor Illich, which has been really leading the way on all these efforts. I know he's been putting a lot of effort. So thank you very much. Please give them an applause, because he's been. And yeah. One, and with that, I really hope that this week is an amazing experience, that it really helps to build alliances, community, and of course to inspire, create new ideas, new solutions, and new friendship. So please enjoy the week, and welcome to UNAM and to Mexico City.
Uy, pero... ok.
Dale, 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 dale. Dale, dale, tú sin miedo, tú dale sin miedo. A ver, despláyate. Tú despláyate. Ahorita. Dale, como Dale, al principio. Sí, pues será. Si quieres me la pongo en otro lado. Siempre tratando. Ah, ok, sí. Sí, sí. Sí, sí, dale. Pues, sí, está un poco. Sí. Sí. Ah, ok. Yo aquí al final.
Okay, so thank you again for coming back. So in order to close the first day, we have Borja and Said, who are the cultural event, and it's remarkable because they belong to UNAM. They are, if I'm right, they're students, and we're very happy to have them. So I please ask you a big applause for them. Thank you very much.
Now I'm going to play in the sonata. It's opus 54. This sonata not very known because the sonata is in the Leipzig and sonata. So this sonata is not that great and that known, but it's really beautiful. It has a lot of contrast. The first movement is in tempo de English. So it's like a dance, it's like a station. We can say it's more like feminine, that's part of our femininity. And the other part, it's more straight, it's the harmony, it's more complex. It doesn't stop moving our whole time. So I think it's a great example of from one part where we can be this side, but we can also be this side. So I think that's the beauty. I thought that because I was thinking about that this piece, but the beauty in it is that we can give it the meaning that it has for us as a student. composer. And the first one is a private. It's called, and it's inspired in a town of this time. Used to do a city pop. And so this piece is wants to reflect like a puppet, like a town puppet. So it has a lot of foot changes and also in the cakewalk. It's a very fun piece. And this next and final piece is called Move On, the third piece of a whole series. It's people like beautiful. Now I'm gonna put it on, and the idea is kind of that there's always movement, but around that movement there's a lot of different. And though we have the same kind of movement that we see, we can travel to different places. Also, this kind of music is impressionist, and it has much more resources in MOFs or like acoustic piano. So we do have some limitations with the keyboard, but
Thank you so much. That was an amazing show, guys, and we're very, very happy to have you here. Thank you for all the explanation. Congratulations to you guys. Seriously, it's wonderful to know, and the fact that you are from here is just absolutely fantastic. So with all that said, thank you for being here. Thank you to everyone. And then it's time to go. I'm sorry. But good news is we have a pass. So yes, you won't get lost, hopefully. Thank you so much. See you tomorrow morning. Bye.